Hi, everyone, and welcome to Astro at Home, presented by Discover the Universe. Really excited to introduce you to our speaker today, and I just want to do a few housekeeping notes before we get into it. As a reminder, we ask that you respect our chat rules, which are essentially not to spam, so don't send several messages at a time, and we ask you to stay respectful, so don't insult anyone, don't say anything rude. If you do those things, then we will delete your message and possibly put you in a 5-minute timeout, which means you won't be able to ask questions for 5 minutes. And that would be really sad because we really want you guys to send us some questions. So please keep that in mind. Our speaker today is joining us from Hawaii. I'd like you to give us a warm welcome for Laurie Rousseau-Nepton, or Laurie, who's joining us from the Canada-France-Hawaii telescope.
Thanks, Sensei. Hi, everybody. So happy to be here with you guys today. I am actually from my backyard because probably like most of you, I'm still in quarantine. So you might hear some birds. You might even hear the dog of my neighbor. It's the surrounding sounds for this morning. And it's about 8 o'clock in the morning for you. Maybe some of you are still in the morning, some of you are in the afternoon, so good afternoon. And I have prepared a very nice presentation for you guys today. I'm going to talk a bit about what I do here as a resident astronomer. And also, I'm going to talk about my science, which is about how stars forms in the universe. So how the universe is making new stars and how it has always been making stars. So without waiting furthermore, I'm going to start sharing my screen. Okay, awesome. I hope it's working well for you guys at home. So this is a few pictures actually of me by the telescope, the Canada-France-Hawaii telescope, on the summit of the Mauna Kea, which is the tallest quiet volcano in Hawaii. And there's about 13 telescopes, 12 of them that are actually operating, so still observing at the summit of the Mauna Kea. And I've moved here 3 years ago to start working. And just a little bit of background and tell you a little bit about me before I start. So I am a member of the Pequot-Kanunuats Nation. It's a little bit further north from Quebec, close to Masteriats. Basically, when I come back to Quebec for my vacation, I like to come back in September and participate into the annual hunt, the yearly hunt that we have. So I go back with my family, my dad, my uncles, my aunt, and we go hunting moose. This is our camp. It is in a really remote area by a lake, and it is fantastic because I can spend time in the nature. This is a picture of my hand by a wolf track. So it was a really big wolf track. And also I got lucky about 2 years ago, I found an arrowhead right in the lake in front of the camp. And it's amazing to me that we can still find objects like that in such remote areas, which is like a proof of the fact that our ancestors were everywhere and hunting everywhere and fishing everywhere. And it's a beautiful place. And I think as a scientist, my journey started kind of into spending time in the nature. I was observing everything around me. I always like to understand how animals or the plants or even the weather was working. So it was very natural for me as a kid to start looking at the stars, and eventually I heard about this wonderful job that is to be an astronomer, and I just wanted to study physics and the stars. And when I went to the university to study physics, and then started a master program in astronomy, I went observing at the Momigantic Observatory. This is a picture of me with a couple of other students. Back then, I was actually a senior student, and I was training other people in using the telescope. And I spent a lot of time there, and we had a lot of fun doing science and testing different cameras that we put on the telescope to take images. And I graduated not so long ago in 2017. This is my supervisor, Kamel Rabat, and all the other students that were doing their PhD at the same time I was. So we had a really nice team. And as soon as I finished, I went to Hawaii. So big trip. About 2 weeks after I defended my thesis, I moved in Hawaii, which is right here in the middle of the Pacific Ocean. And Hawaii has multiple islands, but I live on the Big Island, which is this one right here. And the Big Island have 5 volcanoes, 3 of them that are considered as active. And I live in Waimea, and I work in Waimea in the north of the island by the biggest mountain, the Mauna Kea, where the telescopes are. And this is a very nice picture taken from our headquarters, our office in Waimea of the mountain. And the telescope right there on the left is the Canada-France-Hawaii telescope. I think we have the nicest spot on the island. And I see I have a question on the chat, so I'm going to take it right away. How many people works at the Canada-France-Hawaii? So we are about 45 to 50 employees. It varies through the year. Sometimes we have interns and students that come to make project with us. So yeah, it varies a little bit. And do we ever stay overnight where I work? So there are a remote observer that stays overnight. It's just 1% that do the all night. But as an astronomer, I'm planning what they're going to observe on the skies. So I send them an email with a detailed list of the things that we're going to look at, and I make a plan using a software for that, and then they point at the sky. But I am on call, so if they have any problems or any questions, they have to call me in the middle of the night. And sometimes, for special occasion, I will stay up because we're doing special tests with the cameras, special tests on sky. So then I stay up with them, make sure that everything goes well. Okay, this is a picture of the telescope, and I like to show that picture because we can see at the summit, we are actually most of the time above the clouds. And we can observe most of the time. Since the cloud cover is down there, it's not a big problem. It's actually a good thing because those clouds are actually blocking the light from the towns nearby. And it makes the sky looks darker up there. So it's blocking the light, what we call the light pollution. And the skies, the summit of the Mauna Kea is really, really dark. And that's inside the telescope. So I selected that picture because there is one camera at the bottom of it right here, which is my favorite instrument. It's called CITEL, and this is me pushing CITEL when we are changing the instrument, changing the camera. And this is actually CITEL once it's installed on the telescope. It is my favorite camera because when I was in Quebec doing my PhD, I was actually working with the team that developed and built the camera that is coming from Canada. And it's a unique instrument, and I'm going to show you a little bit later on what kind of science I do with it and also what kind of data it takes. But we developed it in Canada, and we actually had a prototype of that camera at Mont Mégantic Observatory, which was called Espion. And I tested that prototype, and then we built CITEL. And then as I finished my PhD, I moved basically with the instrument almost that got installed about the same time I was finishing. So I also want to say that we are in the Hawaiian environment, so it comes with a little bit of challenges, including sometimes a volcano eruption and earthquakes. So this is also a video showing so it's basically the summit of the Mauna Kea in a storm, and I'm going to play it. And if you're looking here, you're going to see some lightnings that just fell on the neighboring telescope. It was Gemini in that situation. And so we got a couple of technical problems because the lightning fell on the telescope beside us. And I see that there's a question.
I was just coming to tell you that for some reason your screen isn't refreshing, so we can't see the new pictures. It's still on your first slide. Yeah.
From the beginning?
Yeah.
Oh no.
It took me a minute to realize you weren't talking about the same photo anymore. So I don't know why.
No, yeah. Oh no, that's so sad. Give me a second. Okay,
Okay.
I'm gonna restart this the share screen.
Okay.
Okay, share. And then let's see. Can you see the second slide now?
I can. It's your full desktop though at the moment. Okay. Yep. If you move, can you move your slide forward and I'll make sure it goes with it?
Yes.
Yep, that worked.
It worked. Okay. Well,
Yeah.
so quickly, this was a couple of pictures of my hunting camp with the wolf track and the arrowhead I was talking about. And okay, I'm gonna move a couple of other slides. So this was the Momigantic Observatory, all the students, my graduation, my trip to Hawaii. It's probably refreshing slowly, so I hope you're gonna see them with a little bit of delay. And now the islands of Hawaii. Yeah, let me know, Lindsay, if it's still a big issue. And now the mountain, and I was saying that CFHT Canada France Hawaii telescope is the one on the left, and the summit, the telescope, and the camera, Citel, the camera right there. And I hope you got all of these images, and it makes more sense now with what I was saying, earthquakes and volcano, and now the video. So yes, so the lightning fell on Gemini, the telescope right beside us, and it created some issues with our instruments. Our instruments were kind of broken for a week, and we had to fix them because of those lightnings. And just to put us now in the mood for talking about astronomy, this is a video of the night sky up there. We have a camera that is actually looking all the time at the horizon, just to let us know if there's some clouds coming in. And it also takes really nice videos of the stars moving above our heads. And now today, so okay, I want to talk about how the stars are forming in the universe. Studying the universe, studying astronomy is all about studying fundamental forces. And I like to say, you know, if you don't know what is a fundamental forces, maybe you have seen the movie Star Wars. It was the Star Wars Day, May the 4th, just 2 days ago. So I think maybe some of you got a refresh by watching one of those movies. But so in Star Wars, you have that force that the Jedi are using to make object moves. We can see it. They can only control it with our minds. It's a movie, but there are actually forces in the universe that we can't see and that are making objects move. And the one that maybe most of you guys know is gravity or gravitation. And this is the one I'm gonna mainly talk about today. So gravitation is that force that makes every particle, every piece of matter of the universe attract each other. So that's why the planets are rotating around the sun. That's why galaxies are forming, and so on. And there are other forces that I'm not really going to talk about today, but I think that this one that most of you guys don't know is the strong nuclear force is the reason why stars are shining. So the very reaction that happens in the very core of the stars, the nuclear fusion that produces all the light and is the reason why those stars are shining is that strong nuclear force. To be able to get to how stars form today, we have to go back in time. So our universe is about 13.7 billion years old. And it started in a very, very small little point, and it started expanding. And as it was expanding, everything that was in it was changing, was getting transformed by the fundamental forces. And at about a few, like hundreds of million years old, which is about that area here, gravity created small galaxies in which some stars started forming. And I have this first video that shows a little bit all the particles in the universe back then when there was nothing that started interacting with gravity, creating structures, filaments, and then galaxies. And in this video, all the little points are actually huge galaxies full of gas and eventually stars. And if we would zoom into a little bit, like a little part of that universe and look into what's happening in detail, we would see a lot of galaxy collisions. So galaxies that are merging with each other. And now this video shows a little bit what's happening. So you can kind of imagine small galaxy that might look like that. So they're really small, very irregular. They're not like big spiral galaxies. And they form stars, and they merge because of the gravity. And they create larger and larger and bigger galaxies, up to eventually a point where you have some spiral galaxies also, just like the Milky Way, that are formed, in which a lot of stars are forming. Thousands, billions of stars are forming. And so since I was saying, like, it all started about a few 100 million years after the beginning of the universe, this is a video that focuses on how those stars were forming. So you have this little galaxy here just starting to form, and all those little blip or flash are actually newborn stars that forms from the gas. And there's a lot of them, thousands, billions of those new stars. And the universe was really active at forming stars when it was young. It is still today, but it was more active back then. And this is another video that shows a lot of the gas, and this is a really active galaxy. And I don't know if you see those bursts, like the galaxy kind of it almost looks like it's exploding. I'm going to replay that part right there. Yeah. So when you see a moment like that, it is mainly due to the supermassive black hole that is in the very center of that galaxy. And we know now that most galaxies have a supermassive black hole in their center that might look like something like that. And this supermassive black hole might have like 1,000,000 times or 1,000,000,000 times the mass of the sun. And when a supermassive black hole is feeding or is like absorbing gas or absorbing a star, let's say, around it, it bursts and creates a lot of energy. And this is actually a real picture of a black hole that we took using a telescope on Earth. It's the first ever image of a black hole. And it was released last year, and it was observed using a grid of telescopes from around the world. And all those telescopes, there were some in Hawaii, SMA and GCMT. Those two telescopes are in Hawaii, and there are telescopes everywhere in America and in Europe, and you can see Greenland and Antarctica. And all those telescopes kind of joined together to take a picture of that black hole. And when it happens, so when that black hole is feeding, it creates those jet of like high energy particle. And when that happens, it kind of push the gas around, and it actually kind of prevent any stars to form for a period of time, like about a couple of million years after that, there won't be any stars that are forming. But today we're going to focus on when stars are forming. So this is a picture of a galaxy, a real picture from the Hubble Space Telescope. And those little guys, the red little blob around here, are actually star-forming regions. So where some gas is getting affected by the gravity, it collapses and forms stars. And we're going to check what's happening. So I have this nice video here, which is a simulation of what's happening in the gas. This is a cloud of gas. And in that simulation, it's a computer simulation, they kind of induce a little bit of a push to the gas. And then they let the gravity equations and how the gravity should affect the gas kind of go. And then they look at how many stars are forming into that gas. And all those little white blob here are newborn stars that formed from that gas. And out of a cloud of gas like that in a galaxy, you can form maybe 1,000, maybe 10,000, maybe 100,000 stars out of just one cloud. And the cloud will also collapse in about a few million years. So it will take maybe up to 1 to 4 million years for a cloud like that to kind of collapse and form those stars. And this is what you end up with. so this is a cluster of newborn stars. They're usually more blue, and around it you have the gas. This is kind of a nice one, like it's almost spherical. It's called the Rousseau-Nepton Nebula. But I also like to say that and to show that it's not always perfectly circular and round like that. So this is another video that shows a similar simulation of when the stars are forming. And you can see here that stars are forming a little bit everywhere in that cloud. And also it's really filamentary like structure. And we actually see regions that are have newborn stars that actually look much more messy, much more like this. This is a picture of the star-forming regions in the Large Magellanic Cloud, which is a nearby dwarf galaxy. And it is actually very, very intense, and there's thousands of stars in those regions. And now let's take a closer look at newborn stars. So here's what we call an open clusters of star. So an open cluster of star is usually young, has a lot of blue stars. And if we would look at each stars one by one, and we tried to find out what they look like and what is their mass, we would find out that only a few of them are actually very, very massive, very big. And when I'm saying big, I'm talking about like 40 times the mass of the sun, maybe 100 times the mass of the sun. And those stars are actually really important for what I'm doing, for the kind of science that I'm doing. And I saw that I missed a couple of questions now. Okay, so if stars stop forming, then how would this affect our everyday life? Oh, that's a good question. So right now, stars are forming in the Milky Way. They are forming in our galaxy because we don't have like a very active black hole in the center eating right now. There is a black hole, but it's not feeding right now. There are some proof or some clue that our black hole was feeding about 6,000 years ago, but just a little bit. So it didn't really stop any star-forming regions to be active. Okay, how big can this beautiful cloud get? So those star-forming clouds are really huge. They are about 100 light years big. So a light year is billions of kilometers. So it's just to give you an idea. And a cloud like that is 100 light year. And a good way to see it is that the speed of light is 300,000 kilometers per second. So every second, the light can travel 300,000 kilometers. So if in 1 second is 300,000 kilometers, can you imagine how much distances the light can travel in 1 full year? So a cloud like that is about 100 year of light traveling into the universe. So that's a really, really big cloud. And it can also, so in those area where you have some massive stars, you can see supernovae. That's one of the questions. Okay, how big can a supernova get? So some of the stars have like enough mass, like maybe 20 times, 40 times the mass of the sun. Everything above that will end up exploding in a supernovae. And I think I have a couple of I think I have a video later on that will show what happens. And a supernova is about a couple of, depending on its age, because it's like an explosion, it can be maybe 100 times smaller than the clouds that we just see, maybe like 1 light year big. But now I'm gonna go back and we're gonna see some videos here of what's happening in the gas when a massive star, like the one that will end up being a supernova, when those massive stars are starting to shine. When they start to shine, they heat up the gas around them and they create gigantic bubble of warm gas that is warmed by the UV, the ultraviolet radiation from the massive stars. And this is a bubble that would be created by a star that is about 10 to 20 times the mass of the sun. But if it's 100 times the the mass of the sun, then it creates a larger bubble and much more quicker as well. So in about like 30,000 years, you have this gigantic bubble of warm gas that is created. And this is actually what I observe as an astronomer. I observe regions in galaxies that look like that are actually giant bubble of gas that is warmed by really massive stars. And this happens all the time in galaxies. Like I was saying, it takes about a few million years for those regions to form stars. But in a galaxy like the Milky Way, a spiral galaxy, and this video is actually accelerated a lot. To give you an idea of the time scale, a galaxy like the Milky Way makes one turn on itself every 250 million years. So one turn is 250 million years, 250 million years. And those little red blob that we see like popping are those star-forming regions that have some massive stars that create those hot bubble of gas. And then we see this red blob when the gas is heated. And we can see them at large distances because they're really bright. And so it also happens through the spiral arm of the galaxy. We saw, like in that video right there, we saw that most of the star-forming regions are actually following the spiral arm of the spiral galaxy here. And so when a cloud of gas enters the spiral arm of a galaxy, it gets more easily kind of compressed by gravity. It forms the star, that kind of big bubble of gas that lasts a few million years. And then eventually it pops out and we only see stars, and it doesn't shine as much as when it was young. So now we're gonna go back to one of, well, actually my favorite constellation. And I have this picture of the night sky. If ever you look outside at night, tonight or this week, you might be able to see the Orion constellation, depending on when you go out. This constellation right here has also 3 stars that we call the Orion belt in the middle. And if we focus into the lower part here, so this is the Orion constellation, you have what this area here, which would be the Orion sword, that has a nebulae right here, the Orion Nebulae. And the Orion Nebulae is a star-forming region. It's the closest star-forming regions that we have from us. And I have this nice videos that is kind of traveling through the Orion Nebula here. And the Orion Nebula is very close to us, so it's a good object to study, but it's only a few star-forming regions are actually close enough from us to see all the details and everything. So as an astronomer, when I want to observe a lot of different star-forming regions, I have to go outside of the Milky Way. I have to observe star-forming regions that are in other galaxies, and that's what I do. So I'm gonna just go a little bit further in that video, and we're gonna kind of dive into the Orion Nebulae right here. So you see the cloud of gas, you see the stars in the middle here, and you can imagine that most star-forming regions look like that. So the newborn stars are quite blue, they're in the middle right here. And I see that some questions are popping out. Okay, how many Canadian at the Canada-France-Hawaii telescope? We're about 10 Canadian. We have engineers that are from Alberta, astronomers from Quebec, and we had astronomers from Victoria and in BC. And yeah. So can a star be invisible? That is also a good question. Yes, a star can be invisible. It can be hiding into a cloud of gas. Like this one here is almost invisible. There are stars that we can't see because there's too much gas in between us and the star. Okay. So now this is the Orion Nebula. We just saw it in really big and a lot of details. And this region is actually like quite big. It's about a few light years across. And this is another galaxy close by that we observed with the camera CTEL. And there is a lot of star-forming regions of different size in there. And just as a reference, this big guy here is about 25 times bigger than the Orion Nebulae. So it's a really big star-forming region. And can a supernova be invisible? Oh, that would be impossible. The supernova is like one of the brightest events that ever happened. So it's so bright, everybody can see it. We can see it at so large distances that we actually use supernovae to calculate distances of very far away galaxy because we can see them. Okay, and this is two other galaxies with star-forming regions. This one is about 250 times bigger than the Orion Nebulae. This guy here would be about the same size as our little guy that I just showed you. And in this galaxy, this guy, which is about 25 times bigger than the Orion Nebulae, would be looking like a dot. And the Orion Nebulae would actually not be visible at all. We wouldn't be able to detect it. So they have thousands of star-forming regions that are active in those galaxies. And why do we study that? Why is it so important? So the gas is forming those stars using gravity, and eventually those stars might explode in supernovae. They have winds, they push a lot of gas around them, and this gas returns to the galaxy and can then be used to form new other stars. It's a cycle. So stars are formed, they live, some of them explodes, they return gas to the galaxy, and it starts again. And when they return the gas is transformed because the star is doing that reaction in its center, the fusion of the nucleus. So it creates elements that are bigger and bigger. And this is so if you're familiar with the elements that we know in the universe, you might have seen the periodic table of the elements. You might know elements like hydrogen, like oxygen that we breathe. You might know the carbon, the aluminum, the iron. So all of these elements are what we know and it's building things around us. And the universe, as it was very young, just after the Big Bang, was mainly composed of hydrogen and helium, and everything else has been produced by stars. So as the stars kind of burn helium and hydrogen, they form new elements and creates all the chemical diversity we see in the universe and kind of spread this. And then other stars like the sun can form through this new material, form planets and form other things that wouldn't have been possible to form at the beginning of the universe. Can we see invisible star with infrared light? That is a good question. So infrared light can pierce the cloud, can go through clouds. And so if a star is embedded in a cloud, you might be able to see it a little bit in the infrared. Well, you have much better chance to see it in the infrared. Nevertheless, if it's too thick, the light will still be absorbed and you won't be able to see it. If there were no supernovae, what would happen? Oh my God, we need those supernovae to exist. Those supernovae, those stars that are exploding, is the very reason why we are on Earth and why the Earth has so many heavy elements like iron and nickel and everything that is in the core of the planet is basically elements that are produced during those big explosions. So we need supernovae to exist. Okay, and yeah, you remember I was talking about Orion? It's my favorite constellation. It's a winter constellation. There's a special star there. It's a little red, and actually, if you find the constellation in the sky, you can see it by eye. It is redder, and believe me, you should go out and check it out later today. It is a really red star. It's called Betelgeuse. And Betelgeuse is a massive star. It is in a phase where it's kind of blowing matter like that. And eventually, Betelgeuse will explode in a supernovae. But we don't know exactly when. Can happen tomorrow, can happen in 100,000 years. But believe me, when I go outside at night, I always take a look at Betelgeuse just in case I would be able to catch it as it explodes. And it wouldn't be dangerous, but it would be definitely beautiful to see. When Betelgeuse is going to explode, you're going to be able to see your shadow at night, just like it was a full moon. So it'll be that bright. And it might also create a very small black hole. So stars like that, when they explode, they might create a stellar mass black hole, which is a tiny black hole compared to the one that is in the center of our galaxy. And So I'm looking at other galaxies. I'm looking at all those star-forming regions, and I'm trying to understand how it is different in different galaxies. What is our sister solar system? Oh, and I have 2 minutes. Okay, so we don't have a sister solar system, but we have a lot of systems around us that look like us. I'm looking at stars that are much, much bigger than the sun. So for my science, I'm definitely not looking at a twin of the sun. But all of these regions and galaxies that I study have really, really big stars, hundreds or 100 times the mass of the sun, or maybe 10 or 20 times. And this is a galaxy M33, and I'm studying that not alone, but with people from all over the planet in different countries. This is my science team. We're about 60, so it's really, really fun because I can work with people that lives in everywhere in the world, and we're studying that so that we can understand how the stars are forming using galaxy nearby, and it can apply, and we can maybe be able to understand what happens in those galaxies right here, the red ones, that are galaxies so far away that they actually lived when the universe was really young, just right after the Big Bang. So those galaxies are really hard to analyze, but by studying objects that are close by, we hope to be able to understand what's going on in those really, really far away galaxies as well. And I'm going to finish showing you what CITEL data look like. So this is a video of a piece of that galaxy right here. And CITEL, which is that Canadian camera, is actually creating nice data cube or videos. And when it, yeah, right there, you saw the galaxy was kind of catching on fire. So we can see the warm gas around the massive stars. And this enables me to study the gas in the galaxy and all the different chemical elements, the carbon, the oxygen, the nitrogen, and everything that is in the gas that has been pushed in the gas by the massive star. And I have students coming working with me often. So if ever you end up at the university or maybe at the end of your high school and you want to do a science project, please contact me. I'm always happy to help people doing astronomy. And I'll take your questions. Thank you.
Thanks so much, Laurie. I know that we've got a ton of questions today that the kids have been sending. And we can't answer them all. They were having like a competition to see who could ask the most questions. So they just kept coming and we did our best. But since we're kind of at time right now, I've asked the kids to send us some telescope emojis in the chat to say thank you for your talk today. They seem to have really enjoyed it and were inspired to ask lots of questions. So that's pretty awesome. So thank you very much for coming today and joining us from the beautiful weather you're having in Hawaii.
Yeah, it was really fun. I hope you enjoyed.
Yeah, we did. We're still getting questions and I'm trying to keep a list of them that I will share with you later so that if you're curious about all the questions we got, I'll send you all of them. Perfect. But yeah, there's just lots coming right now. So I'm a little distracted. Hold on. Okay, so thank you very much for coming. As usual, for those of you who are watching from home, if you're curious about more about Laurie or the work that she does, we've added some links to the description box below the video window here. If you're interested in what we're talking about tomorrow, we have a woman coming to talk about how to sort of create images of space, and it's going to be really interesting. And if you don't want to miss that, then make sure you subscribe to our channel and click the bell so that you get a notification when we go live. And feel free to spread the word. So if you want to tell your friends about our programming, you can go for it. We plan to go until the end of the month, so they can join us anytime. I think that's about all I have to say. So I guess we'll see you guys tomorrow. Thanks again, Laurie, for joining us.
Yeah, thanks. Bye, everybody.
Thanks.
Have a nice
Bye,
evening.
everyone.
Bye.